Welcome to our program, Astronomy for Everyone. Our program this month is about astro-imaging. And with me here in the studio is Gordon Hansen. Hi, Gordon.
Hi, Don. Thanks for having me.
So what about this first segment?
Okay, we're going to talk about lunar and planetary imaging. We have an advantage with this that the objects are very bright, so we get very short exposures, which allows us to use video cameras and take advantage of getting lots of images and be able to stack them together and get a good clear image. So we'll start off by taking a look at some processing. Processing steps. First, we're going to set some alignment points. But the first thing I want to do is give you some appreciation of what the atmosphere does to images, especially at high magnification. So I'm starting this video, and you can see how it's waving around and shimmering due to the atmospheric effects. This is the thing we need to try and counteract if we want to get a decent image, and that's what this software does really well. So first we're going to do is set some alignment points. We'll set one here, and we're going to set one here, and then we're going to apply it. And now the software is going to go do an initial alignment of the frames to get things kind of in its place. This is going to take a few minutes, so I'm going to pause the recording right now and come back to it when it's completed. Okay, the software has completed that step, and now we're going to do a next step, which is called set cutoffs. Let me put this into, and what this does is sets the amount of actual alignment zones. One of the really nifty things about this software is that besides aligning the frames, what it's going to do now, and you can see the zones that it's created on this image, it's going to find those frames that are the best for each one of these zones and then combine them together. So it's a bit of magic that's going to happen here. So we're going to set the points, and we're going to now calculate the quality level of each one and find the frames that really work. Again, this is going to take a minute or so, so I'm going to pause once more. Okay, that that step is complete, and it took about a minute and 22 seconds. We're now going to go on to the next step, and we're going to align the reference points. So it's going to now start doing some more calculations, and you can see it now moving into each of the zones and aligning those particular zones together. Again, this is going to take quite a while. You can see this is about a 28, 29 minutes. So we're going to once again pause, and we'll come back when it's done. Okay, that align reference points operation is done. So what's left is do the stack frames. And so I'll start this right now. And what you can see it doing is the software is grabbing those pieces of each frame that met the quality criteria, which I had set to about 10%. So it is only taking those frames and those portions of frames that meet that criteria. So we're going to let this run. This one's actually running pretty quick here. It's only going to take about 2 minutes, but I'll pause until that's complete. Okay, what we see here now is that final stacked image. Again, this is now taking about 2,000 frames to begin with, and we found the best 10% of those frames in each of the zones we saw, and then stacked them together to form the final image. Let me switch to another software package here, and I'll show you the end result of these operations. Maybe again to recap, this image here now was one of the original frames from the video file, and you can see kind of the blotchiness in the background and how fuzzy it looks. This is the frame we just saw, which is as stacked, and you can see how much smoother it looks and how much little more detail is coming out. And then finally, this is a final processed image which has gone through some sharpening processes that we can take through, and some changes in brightening of the image to get at some more of the detail. And you can see how much more detail now has come out of the image. So if we compare this final image to the initial image, there's a big improvement in quality from one to the other.
For more information, please check out our website. And right after Term of the Month, we'll be back with more on astro-imaging.
Welcome to Term of the Month for April 2012. Last month we talked about extrasolar planets, and this month we're going to talk about a specific example of an extrasolar planet, Kepler 22b, which was announced recently. First, the term Kepler is used three ways. It's used for the spacecraft, so it's Kepler, the spacecraft, discovers the planets. We have Kepler 22, which is the star, and then Kepler 22b, which is the planet which orbits the star. And so first we'll talk about the spacecraft. The spacecraft is orbiting really the Sun in a nearly the Earth orbit, and it's looking at exactly one spot on the sky. And what it's looking for, it's monitoring a lot of stars, and it's looking for a planet going across the face of a star, and that causes the star to dim, and so that's the data that it's interested in. Now, this idea of a planet transiting, we're going to have Venus transit the Sun on June 5th. The next time we get a Venus transit is 2117, so this is not to be missed. Now, it turns out that in order to get a planet from a star to cross in front of the star, it has to be, the whole system has to be aligned edge on to us, and there's only 0.5% chance for any particular star system to align with us, and that's why the Kepler spacecraft is looking at 150,000 stars. Now, Kepler 22b, the planet, in this diagram, you can see that the orbit of the planet is smaller than the orbit of Earth's planet, but the star is also dimmer than our Sun, and so the idea is that this planet, if it has water on it, could have liquid water, and as we know, liquid water is thought to be something that you absolutely need in order to have life. Now, is there life on Kepler 22b? Well, we don't know if the orbit really is circular, as in the diagram. It might get really close to its star and farther away. And we don't know if it has an atmosphere or if the atmosphere has a greenhouse. So we don't know if it gets really hot. But it's the best candidate that we have so far, and we expect to learn more very soon. So the star is, Kepler 22, is visible in a small telescope. So in the summer or fall, you could actually see it in as small as a 4-inch telescope. Term of the month for April 2012 is Kepler 22b.
Welcome back. For the second part of our topic here today, we're going to talk about how to get the images and also the process strategies. With me again is Gordon Hansen. And Gordon, there are some basic techniques involved with this for the strategies for astro-imaging?
Yes, for lunar and planetary, since we have really bright images, we can use a webcam and take lots of frames in a short amount of time and use that strategy to kind of beat the atmosphere. When we go to deep sky, where we're taking a lot longer images, where it could be 2, 3, 4, 15 minutes, now we have to rely on some other strategies to get a good image and get the noises down.
So we are basically talking about longer image times?
Yes, longer image time for the deep sky, and actually very, very short for lunar. We're talking 1/60th of a second or even less in some cases.
All right, well, we'll take a look at this next part of our program to show folks how this is actually accomplished.
Okay, the first thing we want to talk about is darks. By the way, the software package that I'm going to be doing some of this processing in is called PixInsight. It's one of many processing packages that are on the market. There are some freeware versions. There are some that more commercial ones that you have to pay for. There's a lot of preferences in this and what works for you, and so you need to kind of grow into this and look at these. I particularly like this PixInsight, so this is the one I'm using right now. Okay, let's talk about darks. Unfortunately, when we take very long exposures, besides the light that's striking the CCD chip or the sensor, The sensor also is sensitive to the thermal environment it's in. And if you were to cover up the front of the telescope or the camera lens and take a long exposure, in this case, let's say 15 minutes, which is not uncommon for an astrophoto, you will actually start building up a signal or what appears to be light on the sensor, even though no light is actually hitting it. This is a detriment, and it gets in the way of your image, but it's unavoidable. It's part of the physics of the chip. This is a dark frame that's on the screen here, and it looks pretty dark. Doesn't seem to be much going on. But let me show you what happens, and I'm going to do what's called a screen stretch on this. And as we now expand or stretch out or lighten the image, and we've done quite a bit of it with the press of a button I just did here, you can see that there's some things going on in the background. Again, this was a 15-minute exposure, and the camera I use has actually got the ability to chill the sensor to try and minimize some of this thermal load. And you can see this was done at minus 20 degrees centigrade. You can see it up here in the header. But even at that chilled temperature, there are things going on. You can see some pixels, you can see some streaking in the image because different rows of the pixel slightly more sensitive or different sensitivity. There's some other gradations going on, and you can imagine as this is in the background of your image, as you stretch the image to pull out information, this is going to get stretched also. So this is something we want to get rid of, and part of the calibration process is called the dark subtraction. What I physically do is I take each of the frames I take of my image and I subtract the dark frame from it. That pulls out a lot of the average noise or dark signal that gets into the image. Okay, let's now talk about the next thing we want to do, and these are called flats. Unfortunately, it's next to impossible to keep every surface of your telescope and all the pieces of glass and filters that may be involved to be totally clean of dust. They settle out of the atmosphere if they get on it, and they're going to cause some defects. And this is a flat frame, and it's essentially an image taken of a flat white surface. I use a piece of opaque plastic that I point towards the northern part of the sky where there's no sunlight, and it's essentially taking a picture of the optical train. And you can see it's kind of a uniform gray. There's some things you can see on the surface. You can see this dark spot here. That's a piece of dirt that's right on the sensor cover, and there's some other pieces here. Again, let me stretch this to exaggerate what's here. You can see a bunch of things happening now. You can see what we call donuts. These are dust particles that are on a filter or another piece of glass that's further up away from the sensor, and they look like donuts, and that's the way we call them. The closer the dust particle is to the sensor, the tighter it gets and the darker it gets. So you can see some other spots that are in here. You can also see what's called vignetting that's going on in this through this chain. We're brighter in the center or maybe slightly off center here than we are at the edges, and that's true of most optical trains. You don't see it too much in your everyday cameras because the focal lengths involved and the fact that you've got a lot of light in the first place. But this is another defect that we want to try and get rid of as soon as we can in our image processing. Again, this is part of the calibration process. In this case, it's not a subtraction, it's actually a division and a multiplication going on, but we don't need to get into the details. What you need to know is the flats become a very powerful tool for getting rid of some of these defects that would mar ultimately your image. Okay, so let's move right on to an image itself. I'm going to do some demonstration on an image here from a object called IC602. It's also called the Southern Pleiades. And this is one frame taken through a luminance filter, which is, luminance filter essentially lets all the red, green, blue light through. So it's essentially letting all the light through. But in this case, the camera is a monochrome black and white sensor, so it's going to show up as a grayscale image. And you can see some stars in this, but it's pretty uninteresting at this point. Again, let me do a screen stretch in this. And oh, by the way, this has already been calibrated. The darks and the flats have already been applied to this image. So let me do a quick screen stretch. And now what I'm doing is I'm dramatically brightening the image, stretching it is the term we use to show the kind of detail that's hidden in the background. You can see this is in a really rich star field. And you can see the bright stars that are part of this open cluster that's called IC602. But there's also another cluster in the background that's got some interest. And then there's that dark nebulas that kind of put shadows into the image. So this is, like I said, one frame, and by itself, before we've done any processing to it, it's pretty uninteresting. So what we really want to do is we want to now try and bring out the detail. And one of the really powerful ways that we can enhance the image and bring out as much detail as possible, and also get rid of some remaining noise that we don't want in the image that's left over even after the calibration process, is that we take multiple images of the same object, and then we stack them together. One of the ways we do this is through what's called a star alignment process. In this case, for this object that we took 6 luminance images. And what we first need to do here is we need to take each of these images and make sure that all the stars line up with one another. And so this software package has an algorithm in it that looks at all the stars in the image and then moves the images around so that all the stars line up with one another. So let me go ahead and start this process. And the image will start taking the images and start doing some crunching on it. You can see the process window here. This is going to take a few seconds, so I'm going to pause this until it's completed. Okay, that process is done, and just let me give you a little bit of a look at what the software was doing. This is the process window here, and it kind of gives a summary of what's happening as the process is going on. And here's the last of the 6 images. And you can see it found in an image almost 24,000 stars. So this thing was loaded with stars. And what it does is it takes, in this case, took 1,381 stars and matched it to the master frame and aligned things to see how all things lined up. And you can see it only had to move things a little over 1/10 of a pixel, which essentially says it didn't move anything at all, and essentially 0 rotation. So it will not only move the things around, the scale thing around, but they'll also do some rotation if necessary. In this case, it was only 0.01 degrees, which is essentially nothing at all. Okay, so now we have 6 images that have been aligned. And so the next thing we want to do to these is we now want to take these 6 images and stack them together the same way we did with the lunar imaging. Of course, this time we only have 6 in this case, so we're going to get the square root of a 6 as a reduction in noise. These images were taken in a pretty dark, so this is more than enough images to get a decent one from. So we'll go ahead and do this process. Again, this goes reasonably quick, but we'll pause and come back when it's finished. Okay, so the software package now is taking those 6 aligned images and now stacked them together, and it actually averaged them out, and that's where some of the noise reduction comes through. And again, now here's the image, and it doesn't look much different than the individual. Again, because we've done nothing to stretch the image at this point. So just let me show you again a quick screen stretch on this. We'll start again showing what's in the background. Now, I would not do it this quick way. There's some more time-intensive ways of doing the stretching that allow me to bring out more detail that we really don't have time for here. But this shows quite a bit of detail. Now, this is a black and white camera, and black and white is kind of okay, but we would really like to do color. And with a monochrome camera, what that means is we take images through red, green, and blue filters. So this is one we did through luminance, which is getting all the light through it. And we did this at a relatively high resolution because the human eye is very sensitive to illumination changes for resolution and not so much for color. So we do color it at a lower resolution to make things happen faster. But what we'll do is we'll take a red, and let me stretch these as I go here just to show you. So here's a red image. Again, this was a black and white camera, so the red one looks black and white. Here's the green. Stretch this one. And here's the blue one. Again, they all kind of look the same. And they're obviously no color yet. So what we need to do is take the red, green, and blue and combine them together into a color image. And that's what this image now starts to look like. And I'll do a quick screen stretch on this one also. And it's starting to bring out some more detail, but you can see that there's also some color differentials occurring across this image. There's other things that need to be done to this that actually can take several hours of processing work to help correct. But to give you the final picture on this, let me open the final image, and this is the final or near final version of this Southern Pleiades IC 2602, and certainly based on that first image that we took, where there was very little going on, you can see the advantages of the processing and that we can go through to bring out the color, the blueness in these hot young stars and some of these older reddish stars in the background.
Thanks, Gordon. If you have any questions, you can send us an email. You'll see the address at the bottom of your screen. And right after our scroll of upcoming events, we'll have What's Up in the Night Sky.
Welcome to What's Up for April 2012. We will start with the phases of the moon. The full moon is actually on Friday, April the 6th. Since it's the first full moon since the beginning of spring, back in March, the Sunday following, April the 8th, is officially Easter Sunday. The third quarter moon will be on the 13th this month. Then we'll have the new moon on April the 21st, which is great news for meteor shower watchers because of the Lyrid meteor shower, which we'll talk about in a little bit. And we'll end the month on the 29th of April with the first quarter moon. Now we're going to talk about what planets are doing in the nighttime sky, and we'll talk about shortly after sunset. You'll look to the west by southwestern sky where you'll see the brilliant planet Venus. It is the brightest planet that we can see from the Earth. And it'll be a little bit higher in the sky than the largest planet, which is Jupiter, which will be a little lower. Now, Venus takes about 225 days to orbit the Sun, which means it travels faster across our sky, as we see it from the Earth, than Jupiter, which takes nearly 12 years to go around the Sun just once. If you have a pair of binoculars or a telescope, Check out Jupiter and see the 4 largest moons named after Galileo: Io, Europa, Ganymede, and Callisto. Now we're going to go to the southern sky and look for the red planet Mars. Mars is located in the constellation of Leo the Lion. Look for the familiar backwards question mark, which marks the head and the mane, and the punctuation point on the backwards question mark is Regulus, known as the heart of the lion. Our next planet will be up after 10 o'clock at night in April, and that is Saturn. You'll see it low to the eastern sky after 10 p.m., and you will see it next to the brilliant blue star Spica, the first and only blue star of springtime that's easily seen with the naked eye, and in the constellation of Virgo. Now, back in March, we talked about the planet Mercury, which was visible shortly before sunset. Oh, by the way, here's a wonderful close-up of, we'll go back to the Saturn one. If you have a telescope with enough power, you'll be able to see Saturn and some of its wonderful moons, and you can enjoy the awesome rings. Now we'll go to shortly before 7 a.m. for April. Now, you won't be able to see it unless you are very, very careful, because Mercury is now on the morning side of the sun, and it will be lost in the glare of the sun. Here, this is an image using Stellarium software, where you can actually disable the atmosphere and see where Mercury is, not that far away from the sun. So for at least for April, it's going to be very, very hard to see Mercury. You have a better chance in May, although March was actually the very best time to look at Mercury for the entire year. Now, we talked about the new moon on April 21st, which is really nice timing because on the morning of the 22nd is the Lyrid meteor shower. Meteor showers are named after the constellation they appear to be shooting out of, and the Lyrids come out of Lyra the Harp, near the bright star Vega, the brightest star of the summertime. Anytime after about midnight, although 2 a.m. is probably the best time to look to the eastern sky. Look for the 3 bright stars of the summer triangle. The brightest one at the highest part of the sky is Vega. Look just a handful or 2 of fingers away to the upper right for the meteor shower. Vega can usually, the Lyrids can have anywhere from 10 to 20 meteors an hour, although they do have outbursts which can go as many as 100 an hour. That's what's up for the night sky.